All right, lecture 3.2, independent and mutually exclusive events. Independent events. So two events, A and B, are independent if the knowledge that one occurred does not affect the chance the other occurs. So for example, the outcomes of two rolls of a fair die are independent events. The outcome of the first roll does not change the probability for the outcome of the second roll. So let's look at that in action. Let's let A be the event of rolling a 1 on the first roll, and let B be the event of rolling a 5 on the second roll. So probability of A and B is the probability of rolling a 1 and then rolling a 5. So the probability of rolling a 1 is 1 out of 6, as is the probability of rolling a 5. So to compute how to find the probability for rolling a 1 then a 5, we actually are just going to multiply them together. That is because whatever roll I get on the first roll, it doesn't affect the likelihood of getting a 5 on the second roll. That's the idea of independence. So the probability of A and B, which is again probability of rolling a 1 and then a 5, is just going to be 1 over 6 times 1 over 6, which is 1 over 36. So the idea behind independent events is that the probability of an AND situation, or the probability of an intersection, is just the individual probabilities multiplied together. So let's look at another example. Suppose that 50% of people own dogs. If we pick two people at random, what is the probability that they both own a dog? So we're going to let A be the event that the first person owns a dog, and B be the event that the second person owns a dog. And we're going to assume that one person owning a dog doesn't affect the likelihood of another person owning a dog. So these events are independent. Therefore, the probability of A is 0.5. So I got that from my 50%. I convert it to a decimal. Probability of A is 0.5. Same with probability of B. So I take 0.5 and multiply it by 0.5 to get 0.25. And that's the probability that picking two people at random, they will both own a dog. All right, so not all events are independent though. So let's consider that Lacey draws a 3 from a standard deck of 52 cards. Then without putting it back, she proceeds to draw a second card and gets a 4. So we want to look at A as the event that Lacey draws a 3 and B as the event that Lacey draws a 4. So we kind of want to know if these are independent events or not. I hope it feels like they're not independent, because when you don't replace that card, the likelihood of your drawing a 4 changes. So in general, drawing a 3, event A, there's 4 ways to do that. You can get a 3 of clubs, a 3 of spades, a 3 of diamonds, or a 3 of hearts. So there's 4 cards that have a 3 on them in a deck of 52. So the probability of A is 4 out of 52. Event B is drawing a 4. And similarly, oh, that should say B, sorry. Similarly, the probability of event B is also 4. There are 4 cards with a 4 on it. So if these really are independent events, right? Drawing a 3, then drawing a 4, it should be the case that the probability for doing both of those, right, a 3 then a 4, should just be probability of A multiplied with probability of B, which would be 1 over 169. But that's not really what's going on here. The probability of A and B is a bit different. So notice that the first term here, 4 out of 52, this is the probability of drawing that first 3, right? Because we have all 52 cards there, nothing's been taken out, there's 4 3s, and there are 52 cards. So 4 out of 52. But the next draw, because we don't replace it, there are only 51 cards left in the deck. So I still have the 4 4s in there, right? Because Lacey drew a 3. I still have the 4 4s in there, but I only have 51 cards left. So I end up with 4 over 663. So these numbers are not the same, right? And what we're saying here is the probability of A and B is not equal to the probability of A times the probability of B. So in this case, we would conclude that A and B are not independent events. In fact, drawing that first card A definitely affects the likelihood of success for event B. So we're going to see a lot more about this when we talk about conditional probability. So let's look at it from another standpoint. Let's say now instead of Lacey, we've got Lucy. Let's do it with replacement. So it's the same thing, right? We want to have A, we draw 3, B, we draw 4. But it's different this time because we're going to draw our card and then we're going to put it back in the deck before we draw our second card. So again, probability of A is 4 over 52, and the probability of B is also 4 over 52. So now what we want to do is compute the probability of A times the probability of B, which is 1 over 169. This time when we compute the probability of A and B, the first guy is still 4 over 52, so that's the same, but notice that the denominator in the second term didn't go down to 51 like it did previously. That's because we are replacing the card. So this act of replacing the card before drawing another gives us that the probability of A and B is equal to the probability of A times the probability of B. So we see that here A and B are independent events. So let's look at some special cases. So this is commonly called at least one. So this only applies for when we have independent events. In a large population, 52% of the people have been vaccinated. If 5 people are randomly selected, what is the probability that at least one of them has been vaccinated? So first we're going to lean on our friend, the complement. Let's set it up though. The probability of being vaccinated is 0.52. Probability of not being vaccinated is, this is the complement, right? So the probability of the complement, it has to be the opposite. It's the other piece that makes it whole. So if 52% are vaccinated, that means 48% are not vaccinated. 52 plus 48 is 100. So that's where this comes from. All right. So now we have one use of the complement, and I think we're going to use it a second time too. So at least one means that I could, if I met one person, if I selected just one person who was that was vaccinated, that would satisfy, but I could also select 2 and that would satisfy, or I could select 3 and that would satisfy. I could also select 4 or 5 and that would all satisfy. So in order to do that, I'd have to do the probability of exactly 1 plus the probability of exactly 2 plus the probability of exactly 3. Well, that's just like a lot. So I'm not going to do that. I don't want to have to compute 5 probabilities. So what I'm going to do is I'm going to take the complement, because the opposite of at least 1 is none. So if you pick 5 people randomly, it could be the case that none are vaccinated, all are vaccinated, 1 is vaccinated, 2 is vaccinated, 3 is vaccinated, or 4 is vaccinated. You have 6 possibilities. So since 5 of them are my favorable outcome, that means just 1 of them is unfavorable. And I'd much rather compute 1 thing than compute 5 things. So I'm going to compute the probability that none of them are vaccinated. Then I know that the probability of none plus the probability of at least one has to equal 1. This is complements. I'll use that to say that the probability of at least 1 is 1 minus the probability of none. So again, I'm going to compute this, the probability of at least 1, by just computing the probability of none and then subtracting that from 1. All right, so probability of none, that means nobody is vaccinated. And since these are independent events, I can just multiply these individual probabilities together. So the probability that you're not vaccinated, followed by another non-vaxxer, etc., and so on. So this equals 0.48 multiplied together 5 times. And repeated multiplication is the same as exponentiation. So I can actually just write this as 0.48 to the 5th power. So the probability of none is 1.48 to the 5th power. Thus, the probability of at least 1 is 1 minus that 0.48 to the 5th power. And that gives me my final answer of 0.9745. In general, this is the form for at least 1. So notice we had 5 people randomly selected and my n was 5. If I had done 10 people randomly selected, this n would be 10. Mutually exclusive events. So A and B are considered to be mutually exclusive events if they cannot occur at the same time. So this means that A and B do not share any outcomes. And in particular, it means that the probability of A and B is 0, right? Because A and B cannot happen. If we go back to the first slide, we'll see that if something cannot happen, the probability of it is 0. If they can occur at the same time, then they're not mutually exclusive. It seems kind of like an obvious statement, but we'll use it in a second. All right, so let's be, okay, let's let A be the event of rolling a 2, and then B will be the event of rolling an odd number. So the probability of A and B is the probability of rolling an odd and a 2 at the same time. So you're looking to roll an odd 2. Well, there are no odd 2s, all the 2s are even. So this is 0, right? This cannot happen. You cannot roll an odd number at the same time you roll a 2. So we see here that the probability of A and B is 0. So we say that these are mutually exclusive events. So let's look at another example. A can be the event of rolling a 3 or less, so that's a 3, a 2, or a 1. And B is going to be the event of rolling an odd number. So the probability of A and B is the probability of rolling a 1 or a 3. So 1 and 3 are the 2 favorable outcomes for satisfying both conditions. They're 3 or less and odd. So I have 2 out of 6 ways to do this, which is 1/3. Certainly 1/3 is not equal to 0. So again, we use this idea of mutually exclusive events and the probability being 0 to conclude that the events are not mutually exclusive.